Hello and welcome to this lecture, students. So till now we have discussed various aspects of testing. What are the types of testing? What are the fault models? And how we can generate the test patterns? How we can apply those test patterns? And how we can actually, scan the results and observe that results. The other important term along with testing in VLSI circuit design is the verification. So it comes along the testing. So let me briefly tell you what is the basic difference between verification and testing first before we go ahead with this topic. Now the first thing you need to understand that verification is done to ensure the correctness of the design, and testing is done to ensure the correctness of the device. This is the basic difference. Suppose you are designing an adder, suppose you are designing a 1-bit adder, then you will see that whether the input is performing in the whether the input is propagating right towards the output in the right manner towards the output, and we are getting the results as carry is generated, sum is generated in the right pattern or not. So logically you will verify the design, okay, that 1-bit adder is correctly working or not. But when we go for the actual manufacturing, then you will test the actual device before it goes to the market, that whether the device is working correctly or not. So one is done on paper and other is done on the actual ground. So verification is done on the paper and testing is done on the actual ground. This is the basic difference. Now the second important thing is verification is primarily responsible for the quality of the design, and testing is primarily responsible for the quality of the device again. Okay, so you have now understood what is the basic difference. Other thing is in case of the verification, we use generally the simulation methods, Karnoff map, you know table simulation methods, and various other tools that we generally use in case of the digital circuits. You already know that. So verification has is done like that. And in case of the testing, we have discussed it in detail in previous few lectures, that how testing process is adopted for the VLSI circuits or any IC. So there are two important steps: test pattern generation and then the actual testing. I mean observing the faults, whether it is faulty or not. I mean the controllability or not and observability. Okay, so let us discuss this thing. Verification tests are usually the first ones a designer might construct a part of the design process. Does this adder add? Does this counter count? So we are actually checking whether the adder is acting correctly, whether the counter is counting correctly. Does this state machine yield the right outputs each cycle? Does this modem decode the data correctly? So we are actually testing the design itself. That is the verification. Okay, so in previous section, uh, since it is a book, so it is quoting from the previous sections. Verification tests were required to prove that a synchronized gate description was functionally equivalent to source RTL. RTL means register transistor logic. Okay, now you need not to go 14.4.1.3 to understand this. Let us understand this at this particular instant only. This book is from Neil and Westy. You can easily go and get it from Google. This is the figure: a functional equivalence at various levels of abstraction. First is behavioral specification, second is RTL specification, third is structural specification, and fourth is physical specification. Now, at behavioral specification, formal verification, test vector equivalents are there, and then RTL specification, both are compared here to get the result. Now, this RTL specification and structural specification, timing analysis and the noise analysis are there. Then the structural specification, and in between the physical specification, we will see a lot of things: layout versus schematic, power analysis, DRC means design rule check, ERC, parasitic extraction. A lot of things are there in case of VLSI. A lot of factors are involved. So in order to have the correct output, correct IC. Okay, so let us move ahead one by one. So in figure 15.1, which I just now discussed, shows that we may want to prove that the RTL is equivalent to the design specification at a higher behavioral or specification level of abstraction. The behavioral specification might be a verbal description, a plain language textual specification, a description in some high level computer program such as C, a program in a system modeling language such as System C, or a hardware description language that you study as VSDL or Verilog. Okay, so behavioral, we are actually designing and deciding the behavior of the circuit. So it can be written in any language, or simply a table of inputs and outputs required, as I discussed the example of the adder. So often designers produce a golden model in one of the previously mentioned formats that it becomes the reference against which all other representations are checked. Functional equivalence involves running a simulator on the two descriptions of the chip, that is one at the gate level and one at the functional level, and ensuring that the outputs are equivalent at some convenient checkpoints in time for all inputs applied. So this is the checking at the reference level or the functional equivalence, you can say. This is most conveniently done in an HDL that we do in case of the hardware description language, you do in case of the VSDL and Verilog. You employ a test bench and see whether the output is generated correctly with respect to test bench. What is the test bench? Test bench is nothing but a test pattern in case of the testing. We have applied so many test patterns and see we have seen so many examples how test patterns are applied and how the faults are checked against that test pattern. So similarly, in case of the VSDL and Verilog, you generate test benches and you check the logic with respect to that test bench, that whether the logic is correct or not, whether the adder or subtractor or whatever circuit, digital circuit you are designing, that is behaving correctly or not. Okay, so the most detailed check might be on a cycle by cycle basis. Increasingly, verification involves real time or near real time emulation in an FPGA based system to configure system level performance. Okay, in situation that is in the actual system that will use the AND chip. So FPGA field programmable gate array will give you the same feeling that as if you are, you have manufactured the device. Okay, so this is recommended because of increasing level of complexity of chips and system they implement. As an example, in the area of wireless local network chips, without a real-time emulation system, it is virtually impossible to simulate the unseen effects of an unreliable channel with out of band interferers. So you first emulate the local area network chips before installing those chips in the field. Before before you are going to manufacture it, you have to verify it whether the chip is behaving correctly or not. This is a behavioral specification, and that is very important. You can check functional equivalence through simulation at various levels of the design hierarchy. If the description is at the RTL level, the behavior at a system level may be able to fully verify. For instance, in the case of a microprocessor, you can boot the operating system and run key programs for the behavioral description. Yes, and however, this might be impractical for a gate level model and even harder for a transistor level model. So if you talk about a system like a microprocessor, you can still boot the operating system and check what are the functionality it is giving, and where the error is there. you know a lot of option is there when you boot the system, but it is not possible in case of the when we talk about RTL level model or transistor level model. So it becomes very difficult. However, this might be this way out of this impasse is to uh, use the hierarchy inherent within a system to verify chips and modules within chips, that combined with well-defined modular interfaces goes a long way in increasing the likelihood that a system composed of many VLSI chips will be first time functional. Okay, so the best advice with respect to writing functional test is to simulate as closely as possible the way in which the chip or system will be used in the real world. So whatever you want to use that system in where you want to use that system, you have to first simulate that in the model itself, whether at the model it is behaving correctly or not. If it is behaving correctly at the model, then you will ensure that it will behave as a device also as well. At least you can logically give the surety about that. But there may be a fault stuck at 0, stuck at 1 fault. That is another issue that will be checked by the testing logics. But here we are talking about the designing of the digital circuits. Now often this is impractical due to slow simulation times and extremely long verification sequences. One approach is to move up to simulation hierarchy as modules become verified at lower levels. For instance, you could replace the gate level adder and register modules in a video filter with functional models, and then in turn replace the filter itself with a functional model. So this is called module by module testing, module by module verification. Suppose you have already tested the adder and you are embedding it inside a bigger circuit. You already tested the adder. So while simulating the complete circuit, you will not check the functionality of the adder because you already tested it. You already verified the functionality, and now you want to check the overall functionality of the chip, overall functionality of that larger circuit. So this is how the module by module approach is there. At the top level, you can surround the filter functional model with a software environment that models the real world use of the filter. So at the top level, just like a Android or iOS application. Android is the software, and at the back end you have the hardware. So the upper one is software. Now applying the software inputs, and you are checking that hardware is behaving correctly or not. You can assume it like that. For instance, you can feed a carefully selected subsample of a video frame to the filter and compare the output of the functional model with what the designer expected theoretically. Okay. So you can also observe the video output on a video frame buffer to check it looks correct or not. So finally, if enough time is available, you can apply all or part of the functional test to the gate level and even the transistor level if transistor primitives have been used. So it depends on your testing time, in verification time, I would say. Verification at the top chip level using an FPGA emulator offers several advantages over simulation, and for that matter, the final chip implementation. Most noticeably, the emulation speed can be near, if not real time. Okay, this means that the actual analog signals, if used, can be interfaced with the chip. Additionally, to assess system performance, you can introduce fine levels of observation and monitoring that might be included in the final chip. For instance, you could include a bit error rate circuit in a communication modem to add performance optimization. This can be done. This can be done in the design. So here we have introduced the basics of the logic verification, and next is the debugging. Many times when a chip returns from fabrication, the first set of tests are run in a lab environment. So you need to prepare for this event. You can begin by constructing a circuit board that provides the following attributes. First is power for the IC and ability to vary VDD and measure power dissipation. Second is real world signal connection. I mean the analog and digital input output, and clock inputs as required to help. It is helpful to have a stable variable frequency clock generator just like a crystal oscillator. And then a digital interface to PC, either serial or parallel ports for slow data or PCI bus for fast data interchanges. So these are the things that requires for debugging. Okay, so you can write, sorry, so you can write software routines to interface with the chip through the serial or parallel port or the bus interface. The chip should have a serial UART, universal asynchronous receiver transmitter port, or some other interface that can be used independently of the normal operation of the chip. The lowest level of the software should provide for picking and poking registers, reading and writing in the chip. An alternate or complementary approach is to provide interfaces for a logic analyzer. These are easily added to the PCB design in the form of multiple headers. These are the things that are required for debugging. We are not going into the details of this particular IC. Okay, so yeah, some other important terms. You should start with a smoke test. What is a smoke test? It involves ramping the supply voltage from 0 to VDD, and monitoring the current without any clock runnings. For a fully static circuit, the current should remain at 0. Analog circuits will draw their quiescent current. Following this, you can enable the clock. Some dynamic current should be evident. Beware that many CMOS chips appear to operate when the clock is connected, but power supply is turned off, because the clock may partially power the chip through the input protection diodes on the input pads. If possible, you should initially run the clock at the reduced speed so that setup time failures are not the initial culprit in any debug operation. Okay, and in case of the digital circuit, you should examine various resistors for health using PC based peek and poke software, again reading and writing. This checks the integrity of the signal path from the PC to the chip. Often designers place an ID in the register at address 0. So peeking at this register proves the read path from the chip. So this is how you can do this, and more details are not required. So it is just elaborating the function of the RTL description. Okay, so you need to know some of the pointers that are important, that are sane for debugging. First is keep an annotated and dated logbook for all the tests done. Second is when postulating a cause for the bug or a test, do one change at a time and observe the result. Okay, in this way you are controlling it and then you are observing it. Check everything 2 or 3 times. Never assume anything unless it is measured and logged in the notebook. Check signals and supply voltages. Double check the specified IO. Never disregard a possible reason for a bug, however crazy, unless you can prove it is not the cause. Okay, use freeze spray or a heat gun to cool down or heat up a circuit to check for temperature problems. So a lot of problems are there. You need to ensure that your chip is behaving correctly, and check the state of any internal registers against that noted in the documentation. Evaluate the timing of any inputs and outputs with respect to the clock. Often setup or hold times can be violated in a new test setup. Okay, so these are the things. When a bug is discovered and corrected, hunt for other portions of design and see whether there is any bug or not. Never assume anything, question everything. A slight touch of paranoia helps. You have to doubt everything like a policeman. Understand the system, make it fail, find a way to elicit a bug. A repeatable method is preferable. So you have to program your circuit like that. If any bug is there, how it will behave, and accordingly you need to again reprogram that. Okay, so you have to have the second I think the method or the way that how your circuit will come out from the error if any bug is there. So this that your circuit should not be I mean your circuit should not be there held in the loop of the error or bug. It has to come out from there. So quit thinking and look. Propose a test and investigate. You can start eliminate possible sources of problems. Divide and conquer. Use hierarchy to eliminate known good parts of the system, as I told you in the just now in the previous page, that you can divide the uh, circuit at hierarchical level and start from the lower to upper level. Keep an audit trail. I mean, check the logbook, check the plug, get a fresh view. If you did not fix it, it is not going to fix it unfixed. Problems do not mysteriously fix themselves. If you find a problem, verify it with simulation to prove your hypothesis of the failure mode. This is the basic debug principle that is required to check the IC. So possible deviation from simulated circuit occur in following tests. Circuit is slower than predicted. Fix slow clock or race VDD. Circuit has a race condition. How to fix it? Heat and heat gun if a logic gate cause race. Okay, circuit has dynamic logic problems. Fix, do not do it again. Generally crosstalk problems, get better tools. Wrong functionality, do a better job for verification. This is how the possible deviations are there to completely check your IC that you are going to manufacture. Okay, so these things that we discussed are the basic part of the IC design in terms of the verification. Okay, Let me also discuss the manufacturing tests, because manufacturing tests are something that is a layer to layer shorts, discontinuing wires, missing and damaged wires, shorts through the thin wires. These are the things that we do in case of the testing. So today we are not covering the testing. We have already covered the testing in detail. Okay, so you only concentrate at 15.1 and 15.2 of your this particular chapter to understand the verification from the book of Univesity. Thank you for listening and watching this lecture.